In our previous video, we showed how lines can be represented mathematically through the use of vectors. And we came up with the vector equation of a line written out here. Before we look at the Cartesian equation of a line, I wanted to emphasize on different notations you might see in textbooks, particularly this one. So for the vector equation of our line, instead of writing any position vector b, we can write it as r. Moreover, instead of writing our direction vector as u, we write it as b minus a, where b is another point on our line. And what we notice here is that we can obtain the expression for our direction vector if we know 2 points. And this makes sense because if we know 2 points on our line, we can draw out a vector connecting these 2 points. And therefore, this will be parallel to our line. And we know that a direction vector is a vector that is always parallel to the line we want to construct. What I want to emphasize on in this video is how we can write mathematically the expression of a line using Cartesian coordinates rather than vectors. And the way we can express the Cartesian equation of a line is by using our vector equation that we obtained in the last video. So if you haven't seen my previous video, I suggest you go take a look at it before watching this video. First, what we need to do is express our general position vector b in terms of coordinates. And to make it as general as possible, we will call these coordinates x and y. Furthermore, we can write down the expression of our position vector a in terms of coordinates m and n. Finally, we need to write down the coordinates of our direction vector u. And I will write these coordinates as minus b in the x-axis and a in the y-axis. And the reason for that will be clear towards the end of the video. As you will see, the Cartesian equation of the line we will write down will depend on these coordinates. And by writing our direction vector as minus ba, our Cartesian equation will be in a clear format. Using these 4 expressions, we can finally write down the Cartesian equation of a line. And first of all, using our vector equation here, we can replace the coordinates of b using the expression. So first, I will write down the coordinates of a, which are m and n. And moreover, we have our ku over here. And remember, k is just a real number. And so it can be either a fraction, an integer, and so on. Therefore, we write k, and then we replace u by its coordinates, which are minus ba. Now, we want to be a bit careful about k here. Remember that k cannot be equal to 0. Because if it is, then we have no direction vector. And if we have no direction vector, then we would have b equals to a, which is just a point. It is not a line. So k cannot be equal to 0. And this notation over here means all the real numbers with 0 excluded. And similarly, u cannot be the 0 vector. If it was, then we would just obtain a point and not a line. If k gets multiplied by our vector u, it means that each coordinate of our vector gets multiplied by the scalar k. Therefore, we can rewrite our expression for b as minus kb plus ka, so positive ka. And finally, we add the coordinates corresponding to the x-axis, so m and minus kb, and we also add the coordinates associated with the y-axis, so n and ka, to ultimately get m minus kb n plus ka. And now what we need to know is that when we have 2 vectors that are equal to each other, their corresponding coordinates are equal, which means that x equals m minus kb and y equals n plus ka. And therefore, we have that x equals m minus kb and y equals n plus ka. And now we have a system of two equations. And what we note here is that k appears in both of these equations. Therefore, by isolating k in our first expression, we can substitute our new expression for k over here. And let me tell you what I mean by that. So here we have our first equation, and we can write it as x minus m equals to negative kb. And therefore, this equals to kb equals m minus x, and hence we have k equals m minus x divided by b. And finally, what we will do is substitute our new expression for k in this expression for y, which yields y equals n plus m minus x divided by b times a, and therefore we get that by equals nb plus m minus x a. Note that here what I've done is multiply on both sides of our equation by b. And finally, what we do is we distribute a in this expression right here. So we have by equals to nb plus ma minus ax. Rearranging the terms, we get ax plus by plus minus nb minus ma equals 0. And if we write this expression here as c, so this is equal to c, we get that ax plus by plus c equals 0. And so this right here is what is known as the Cartesian equation of a line. But what does the Cartesian equation of a line really mean? Well, if we have a point B, which is associated with a position vector B, if our point B with coordinates x and y lies on our line, its coordinates x, y have to satisfy this equation over here. And notice the coefficients of x and y are a and b, which are related to the coordinates of the direction vector u. What this means is that if we have a direction vector associated with our line, we can get the Cartesian equation of our line through its coordinates. And the reason I wrote the coordinates of our direction vector u as minus ba is to get this neat expression over here for our Cartesian equation. So it's just a matter of convention that I wrote the coordinates as such. And our value for c over here actually depends on a point on the line. So if we know a point on the line, for example, a, which is associated with the position vector a, if we know the coordinates of a, we can obtain our expression for c over here because we know that a lies on the line, so it satisfies our Cartesian equation. In a nutshell, the way we obtained the Cartesian equation of a line, the way we derived this expression, is by using our vector equation of a line, and then substituting each vector with its coordinates over here. And then what we get is an expression for the general x and y coordinates of any point on our line. And since k appears in both of our equations, we can write down an expression for k using one of the equations and substituting that into our second equation. And manipulating our expression, we get our Cartesian equation. Thank you for watching this video. Hope you liked it. Leave a comment down below, of course, if you have any questions.